So the algebraic limit theorem talks about the familiar properties we had about limits, that if we add two limits, then it will just be the addition of the two limits, and if we multiply them, it will just be the multiplication of the two limits, and etc. So the theorem goes like this: let limit of a(n) be a, and limit of b(n) be b. Then we have all these properties that first one talks about if we multiply a sequence term by term by a constant c, which is a real number, then the limit of that new sequence is precisely the constant times the original limit of the sequence. And the second states that if we have two convergent sequences that converge to a and b, then if we add term by term of the sequences, and then the limit of the consequent sequence is going to be the addition of the two original limits of the sequences. And third, basically the same thing, but it's the multiplication. So if we multiply each term of the sequences term by term, then the limit of that new sequence is precisely going to be the multiplication of the two original limits. And it also works for division, provided that b is not equal to 0. All right, so we have a long way to go with this proof. We'll start with the first one. Let epsilon greater than 0 be arbitrary. We want to show that there exists n in the natural number such that small n greater than or equal to big N implies that CAN minus CA is less than epsilon, because that's the definition of a sequence converging, and we want to show that the CAN, this new sequence that we have, converges to CA. All right, so observe that the CAN minus CA absolute value is equal to C multiplied by AN minus A. Well, we can pull out that absolute value of C and express it like this. Well, since limit of AN converges to A, there exists n in the natural numbers such that n greater than or equal to n implies absolute value of AN minus A less than epsilon over absolute value of C. So since we know that the sequence AN converges to A, we can make this absolute value of AN minus A small as we want. We can make this expression as small as we want. We can make it arbitrarily small. So we'll make it less than epsilon over absolute value of C. Since C is just a constant, we can do that. All right. Hence, for n greater than or equal to big N, we have absolute value of CAN minus CA, which is, as shown above here, absolute value of CAN minus A is less than absolute value of C times epsilon over absolute value of C, which is precisely epsilon. So we showed that for arbitrary epsilon greater than 0, there exists a big N in the natural numbers such that whenever small n is greater than or equal to big N, the distance between the CAN and the limit CA is smaller than epsilon. Thus, limit of CAN equals to CA for all C in the real numbers. All right, so that's the proof of the first one. What about the second one? Proof 2. So we want to show that the limit of adding two sequences term by term results in a sequence that converges to the addition of two limits in the original sequences. So let epsilon greater than 0 be arbitrary. We want to show that there exists n in the naturals such that small n greater than or equal to bn implies an plus bn minus a minus b is less than epsilon. So observe that this expression is equal to an minus a plus bn minus b, and we can view the absolute value in this way, and by the triangle inequality we have this less than or equal to an minus a plus bn minus b. Well, since an converges to na, there exists n1 in the natural numbers such that small n greater than or equal to big N1 implies an minus a less than epsilon over 2. And similarly, since limit of bn equals b, there exists n2 in the natural numbers such that small n greater than or equal to big N2 implies that bn minus b is less than epsilon over 2. We're going to let big N equal the maximum of n1 and n2. Then, with this choice of n, we know that these two statements are going to be true. Do you know why? Because if we choose the bigger of the n1 or n2, then that bigger n is going to suffice these two statements automatically. So we want to choose the maximum of n1 and n2. Hence, whenever n is greater than or equal to big N, it follows that this an plus bn minus a minus b, we saw that was less than or equal to absolute value of an minus a plus bn minus b. But since that small n is greater than or equal to the big N, which we chose here, we know that this is less than epsilon over 2 plus epsilon over 2, which is exactly epsilon. Thus, limit of an plus bn equals to a plus b. So that's the proof of the second one. What about the proof of the third one? Let epsilon greater than 0 be arbitrary. I'll just write up here what we want to show. We want to show that limit of an bn equals to ab. Alright. Let epsilon greater than 0 be arbitrary. We want to show that an bn minus ab is less than epsilon whenever n is greater than or equal to big N. So we want to find this big N where after that term big N, this inequality satisfies. Observe that an bn minus abn plus abn minus ab is the same thing as this. We're just adding and subtracting abn. So it's these two are actually the same thing. Well, what we can do is we can use the triangle inequality to say that this is less than or equal to an bn minus abn plus abn minus ab. Well, this is equal to, if we on the first absolute value we can factor it by, let's say, bn. So bn multiplied by an minus a, and on the second absolute value we can factor it by a and have a times bn minus b. Well, this is exactly equal to absolute value of bn times absolute value of an minus a plus absolute value of a times absolute value of bn minus b. All right, so we're seeing a similar pattern here as well. Notice that we can make bn minus b and an minus a arbitrarily small as we want, because the sequence an converges to a and the sequence bn converges to b. So we'll go with the easy part first. So there exists big N1 in the natural numbers such that small n greater than or equal to big N implies that bn minus b less than or equal to epsilon over absolute value of a. And this is possible because bn converges to b, and we can make absolute value of bn minus b less than anything we want. All right, so what about the second part? We want to also find n2 in natural numbers such that n greater than or equal to n2, and sorry, this is n1 up here, implies an minus a less than epsilon over absolute value of bn. But we can't just do this because bn is a variable here, as opposed to one we have above. This absolute value of a is just a constant. So we can just make it as small. We can make this inequality smaller than absolute value of epsilon over absolute value of a. But in this case, that's not possible since we have a variable. It's going to work like this. Since the sequence bn is convergent, we know that bn is bounded. And that is from the theorem we proved before. Every convergent sequence is bounded. So there exists m greater than 0 such that absolute value of each term of the bn is going to be less than or equal to m for all n in the natural numbers. Well, then we can use this m as a bound for the absolute value of bn. So we have that. We have that absolute value of bn and an minus a is going to be less than or equal to m times an minus a. Right? This is true because m is always going to be greater than or equal to absolute value of bn. So replacing this absolute value of bn with m yields this inequality. So keep this in mind because we're going to be using this. So now we want to modify this statement we have here up here. Since we weren't able to use this absolute value of bn here because there was a variable, we want to replace it with a m. The m we found here. So I'm going to put this here. So put this down here. So there exists n2 in the natural numbers such that small n greater than or equal to big N2 implies that the absolute value of an minus a is less than epsilon over m. All right, we're almost done. So let n be the maximum of the two n's, the n1 and n2. Then for n greater than or equal to n, it follows that an bn minus ab, we saw that this was less than or equal to an minus a, absolute value of bn times an minus a plus absolute value of a times bn minus b. And this is just from the calculation we did above here, and this part. I just took out, I just pull out this part and then simplified it to less than or equal to this part. All right. Well, we know that this is less than or equal to m times an minus a plus absolute value of a times bn minus b. And this comes from this part above here. We saw that m was the bound for the absolute value of bn. So replacing absolute value of bn with m yields this inequality we have here. All right, we're almost done. Well, then this is less than m times epsilon over m plus absolute value of a times epsilon over absolute value of a. And sorry, I made a mistake here. We should let an minus a be less than epsilon over 2m. And similarly up here, we should make it epsilon over 2 times absolute value of a. So then we'll have something like this, which is then equal to epsilon over 2 plus epsilon over 2, which is epsilon, as desired. All right, so this was quite a long proof, but to summarize it, we are basically first having this inequality. We want to make it something less than epsilon. So adding and subtracting here, a, b, n yielded us to use the triangle inequality to get something like this. And we were able to factor out a bn and an a here to get what we can use. And after factoring out, we get this equation, and we know that we can make an minus a and bn minus b as small as we want, because that is given by the assumption that the sequence an and the sequence bn converges. So then the right hand part of this equation was okay, because the absolute value of a was just a constant. We can find a n1 in the natural numbers such that small n greater than or equal to big N1 implies that absolute value of bn minus b to be less than epsilon over 2 times absolute value of a. And then later on, if we can plug this in here, we would get absolute value of a cancelled, and we will be left at epsilon over 2. Well, that was not the same case for the left-hand side of the equation. Since we had absolute value of bn be a variable, we can't just make this absolute value of an minus a less than epsilon over 2. We couldn't just make it epsilon over 2 times absolute value of bn, because bn is a variable. But we use the fact that the sequence bn is bounded. So then we could find a number m greater than 0 such that m will be greater than or equal to absolute value of bn for all n in the natural numbers. So then we chose a n2 in the natural numbers such that small n greater than or equal to big N2 implied that the absolute value of an minus a is less than epsilon over 2 times m. And then lastly, we chose big N to be the maximum of the two n1 and n2, so that these two statements would be true for small n greater than or equal to the big N. So then we concluded that yielded our final inequality to be less than epsilon as desired. Alright, so if you didn't understand that proof 3, I advise you to go back and read over all of them. It took me a while to realize this proof. It is not easy. I think you have to read it multiple times to understand what's going on. But yeah, that was the part 3 of the proof. Alright, what about part 4? Part 4 states that limit of an divided by bn is equal to a divided by b, provided bn is not, provided the limit of the sequence bn is not equal to 0. Alright, well, if we can show that bn converging to b implies 1 over bn converging to 1 over b, then the red statement we have above, the red statement here will follow from 3, since 3 was about the multiplication of two sequences. And we can utilize that. If we can just show that the sequence bn converging to b implies the sequence 1 over bn converging to 1 over b, then the red statement will follow from 3. So let's show that the sequence 1 over bn actually converges to 1 over b. Let epsilon greater than 0 be arbitrary. We want to show that absolute value of 1 over bn minus 1 over b is something less than epsilon. We want to show this, and this was the pattern for all of the other proofs we had above. So we'll start with this. Observe that this absolute value is equal to b minus bn over bn times b. Well, this is the same thing as absolute value of bn minus b divided by absolute value of b times absolute value of bn. On the numerator, we have something familiar. We can make the numerator as small as possible as we want. So we want to deal with the denominator now. The trick here is that now that we have the absolute value of bn as the variable in the denominator, the trick is to look far enough the sequence. So let's say this is the limit b and 0. So we want to look far enough the sequence such that each term of the sequence is going to be closer to b than it is to 0. So we want all the terms that is further out here. So the trick is this. Consider a particular epsilon naught with its absolute value of b divided by 2. Then there exists big N1 in the natural numbers such that small n greater than or equal to big N1 implies that bn minus b is less than absolute value of b over 2. Alright, since we know that the sequence bn converges, well, that implies absolute value of bn is greater than absolute value of b over 2, right? Consider this. Look at the above picture. Absolute value of b divided by 2 is just the length of the half of the b. So this length is just absolute value of b over 2. There is a point in the sequence such that after all of the sequence after the big N1, we have that these terms are closer to b, closer to the limit than they are to 0. And as you can see, each of these bn terms is going to be greater than the half length of b. So we know that that is true, that exists, such n1 exists. All right, that's going to be key. That's going to be the key of our proof. Now, there also exists a big N2 in the natural numbers such that small n greater than or equal to big N2 implies, let's see, bn minus b is less than epsilon times absolute value of b squared over 2. And you'll see why this is happening right now. Let big N be the maximum of big N1 and N2. Then for n greater than or equal to big N, it follows that absolute value of bn minus b times 1 over absolute value of b times absolute value of bn is less than absolute value of epsilon times absolute value of b squared over 2, since this matches this, times 1 over absolute value of b squared times 2. Absolute value of b squared divided by 2. So, alright, this sounds a bit weird. Why is this happening? Well, we saw that n greater than or equal to big N implies that absolute value of bn is greater than absolute value of b divided by 2. And if we consider this inequality above here, this part, where it is 1 over absolute value of b times absolute value of bn, we know that this absolute value of bn is a number that is always larger than absolute value of b divided by 2. So if we divide a number that is bigger, then we're going to yield a number that is smaller. So consequently, this whole expression is going to be less than 1 over b, 1 over epsilon value of b times absolute value of b over 2, which is this 1 over absolute value of b squared divided by 2. That's what we have here right now. Down here, that's what we have here. So this is simply equal to absolute value of b squared is going to cancel and 2 is going to cancel, and we're just left with epsilon as desired. Okay, so we just proved that a sequence bn converging to b implies that the sequence 1 over bn converges to 1 over b. And combining that with the third proof, we can show that the limit of an divided by bn is precisely equal to a over b, provided that b is not equal to 0. All right, that was a long proof. I believe the first and second proof is pretty straightforward. Didn't need much thinking. But the proof in the third part and the fourth part requires a lot more thinking. It might be hard to digest at first, but if you read it over and over again, you can understand what's going on here. But anyways, that's the algebraic limit theorem, and we just proved the familiar property of the limits rigorously.